Okay, good. Yeah, I can just use that part all the way up to here. All of those options. Okay, good. So yeah, today we are going to continue with this topological expansion. As I said, this is also known as genus expansion. Of GUE matrices. Okay. So as you remember, so we are interested in the following, computing the following thing: 1 over n. We want to compute limit of this trace of a over root n to the power 2n. This is, of course, inside. As n goes to infinity, we want to show that this is equal to Cn, the nth catalog number. And this is the bulk of basically Wigner's semicircle law. So this is for n equal to 0, 1, 2, so on. And so we can put here an maybe. An is n by n unitary ensemble. I mean unitary a by n GUE. This means basically an, if an is aij. I mean, in principle, I have to put an index n as well, but that's okay, you understand. Here, this means that these aij's are complex. So first of all, of course, an star is an, and then aij are complex, standard, normal, random variables. By equal to j. So one of the things that this implies, using Wick's theorem easily, this implies that actually this very fundamental formula, aij, akl, right, is 0 unless j is equal to k and I is equal to L. So we just write it as delta jk, delta IL. These are the delta. This is the Kronecker delta notation, which basically means, yeah, if j is different from k is 0, and if I is different from L is 0. So this, and otherwise is 1. So the value of this expectation value of the product is either 0 or 1, depending on indices. Okay. So we already saw the proof of this for n equal to 0. And
we're looking at the expected value of the trace, right?
Sorry, say it again.
We're looking at the expectation of the trace, right? In the limit.
Oh, yes, 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 of course, yes. Thank you. Yes, exactly. You are really looking at expectation values. Yes, exactly. Okay. Yeah, of course, trace is again a random variable and can take any values, and we are really taking at expectation values. Yes, exactly. So for n equal to 0, n equal to 1, we already checked it yesterday. That's okay. Now let's look at the case n equal to 2. So we want to check that lim of 1 over n trace of an over root n to power 4, basically, in this case, right? This expectation value, as n goes to infinity, we want to show that this is equal to C2. And I believe C2 is equal to 2, actually. So how we compute this? Well, I mean, this is left-hand side is equal to, this is root n to power 4, makes it n squared, and then n is 1. So this is 1 over n cubed. Expectation value of trace of a n to the power 4. Let me allow me not to write n here. A to the power 4. Okay, so this is equal to 1 over n cubed. Now trace of A4, we know what it is. So this is equal to sum Aij, Ajk, AKL, then ALI. You cycle back, right? Aij, JK, KL, LI. The summation is over all I, J, K, L from 1 to n. So in principle, we have n times n times n times n to the 4 indices here, I mean, terms in this sum. Now, what we can do, we can use Wick's theorem to write this, because these are Gaussian. We can write it as sums of products of them 2 by 2 by Wick's theorem, right? So by Wick's theorem then, by Wick's theorem, it's something like this: Aij, Ajk, AKL, ALI. We can write it, we can do different pairings of these 4 places. So it's going to be like the following thing. We can just use this things. So this would be Aij, Ajk, and then AKL times ALI plus we can just pair first and the third one would be Aij, AKL times HAK, ALI, I mean, yeah, HAK, ALI, or we can just do the following, do this and then this. So this makes it Aij, ALI times HAK, AKL. Okay. So what they can do, because taking expectation value is a linear operation, so we can basically bring the summation out and then take expectation value 1 by 1. So basically then this means that this is going to be equal to 1 over n cubed sum over I, J, K, L, of these terms. So this is then becomes 1 over n cubed sum over I, j, k, l from 1 to n of these three terms. Okay? So now we have to see what happens to each of these things. So how we can compute these terms. So now, if you look at these things, in this sum, each of these terms is either 1 or 0. Let's see when it is 1, when it is 0 now. So if you look at this term, this is 1 only if I is equal to k, okay? So let's look at this case. Aij, ajk, then akl, ali. So this is okay, j is equal to j, but I has to be equal to k in order for this thing to be 1, otherwise because it's 0. L is L, then k is equal to I, but that's okay. So we have only one condition. Two of the indices have to be the same, index I and k. Otherwise, they can't be anything. So out of n4, basically, choices, we have n cubed of them equal to 1. So this gives n cubed terms equal to 1. So what does this mean? It means that if you do the summation, so I just write it like this, because I took ijjk over ij is equal to n cubed. This is my very abbreviated notation for the first. Now let's look at this one. Aij, akl, and then ajk, ali. So let's write it. Aij, akl, then ajk, ali. ajk, ali. Okay, so now this is, let's see what is the value here. Well, this is equal to 1 only if j is equal to k and I has to be equal to L. Okay, so j is equal to k, I has to be equal to L. Okay, so what about this one? For this one, a k has to be equal to L and I has to be equal to j for this to be 1. So how many possibilities now we have? So j is equal to k, I is equal to L. Here, L is equal to k, okay, and I is equal to j. So it means that, it seems to me this implies that I has to be equal to j equal to k. Right? Oh, no.
And with L.
But certainly there is an L, so sorry, so a k has to be equal to L, has to be equal to I, has to be equal to j. So all of them have to be equal, it seems to me. Do you agree?
Yeah.
Yes.
Okay. So because all of them have to be equal, it means that there is only n of them that gives value 1, or the rest are 0. So here, so I just write it like this. For the second part, we get sum. Now let's see, aij, akl, ij, kl. So this was, so it's kind of crossing now. These two pairings cross each other. So this gives us equal to n. This summation is n. Now let's look at the last one. The last one, we have got the following term, a I j, a l I, and then a j k, a k l. Now, for this to be non-zero, we must have j equal to L. There's no condition because I already matches with I. The two ends match, so that's good. J is equal to L. For this one, K match, J is equal to L. Again, no extra condition. So we only have one condition in this case. So this means sum. So this pairing I denote by this. Again, this is a non-crossing pairing. This is equal to n cubed again. So there's only one condition, one constraint out of, yeah, so this is. Okay, so what we get here is that, again, I just write it here. So what we get, if we bring this analysis here, we get that this sum is equal to 1 over n cubed times 2n cubed. The first term and the last term each give n cubed contribution. So we have got 2n cubed, and then the middle one is n. So if we now divide, we get what we want, 2 plus 1 over n squared. 2 plus 1 over n squared. Okay? Okay. So we've got 2 plus 1. Okay. Now, what we are supposed to do? We are supposed to take the limit of this guy as n goes to infinity. And obviously, as n goes to infinity, this goes to 2, which is C2. So we checked Wigner's semicircle law for the fourth moment, or moment of degree 4. Any questions about this proof so far? We are trying to find some pattern here. That's all we're doing. Okay, cool. So now we can continue, but it's kind of hard to continue like this. So the next thing is for n equal to 6, for example, or n equal to 3. So we've got, I don't know what notation I use. I want to use, imagine you want to prove 1 over, for example, n, expectation value of sum an over root n to power 6, right? As n goes to infinity, we want to show that this is equal to C3, the third Catalan number. So the question is how to prove this. How can we prove this now? Well, the idea is the same. We just write this. So what we get here, we get this is 1 over n root n. This is n to the power 3 times n. So this is 1 over n4. And then huge sum, expectation value of, now I've got aij, ajk, ajl, alm, ami. I hope I got 6 of them. 1, 2, 3, 4, 5. No, one more. Mn, ani. I hope this is okay. 1, 2, ij, jk, kl, lm, mn, ni. Yes. this sum, now ij, k, l, m, n, I go from 1 to n. So this has n to the power 6 terms. Each of those terms is only 1 or 0. So we have to convince ourselves that this starts with something like n4 with some coefficient, and then other powers are less than n4, so that when you divide by n4, you take the limit, only a leading coefficient here. So our goal is to show now, I just want you to see the pattern that we are trying to prove, show that this is equal to 1 over n4 sum, there is some n4, n to the power 4 factor here, some coefficient that we don't know what it is, plus another coefficient which is going to be less than 4. So it's going to be 4 minus I, some coefficient here. I from 1 up to 4, for example. We want to see this pattern. Finding these coefficients, we are not. If we just show that there is such a polynomial type of expression, we are not interested in knowing these terms, because in the limit they converge to 0. But we are very interested in computing this leading coefficient here. This leading coefficient we want to compute. And of course, we have to show that it really starts with n4 and not with n5 or n6 or this sort of thing. So that's that's the way this game is played now. It's kind of difficult to now count directly like the way that we did. We have to see we have to create some device. So now at this point, people prove this in different ways. So there are several different proofs. One proof that I like is by using maps. So proof using maps. So I will explain what it is. So basically, we are computing 6. So we put a polygon in the plane, regular polygon if you want. Okay, we put a polygon. And each of these edges corresponds to one of these pairings that we are going to depict here, okay? So just choose some pairing, for example, not edges, we are going to identify edges, connect edges like this with that, for example, this with that, and then, okay, so this, and then this, for example. We can do other things. We can just write, this is the polygon again. We can just connect these two, okay? These two and these two, right? We can connect those, or we can connect in the following way. For example, we can connect this with that and with that. So these two are connected, these two are connected, these two are connected. Then what we are going to do, we are going to put indices around this. So here is going to be I1, I2, I3, I4, I5, I6. Here is going to be I1, again, I2, I3, I4, I5, I6. And here again, I1, I2, I3, I4, I5, I6. So now I'm not using these indices I, J, K, L, M, N. So I just use I1, I2, I3, I4, I5, I6 instead of that, because this is something that we can. And of course, there are many other polygons, pairings like that. Okay. Now, each of these things correspond to a. Sorry. Sorry, just this is important. من داشتم زوم می‌کردم. نه مثلا نیست نه بگو الان اونجا این اوکی مثلا بس با برنده اینا بس من میرم خونه بعد چیکار کنم بکن آره 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 میذارم تو اوون درست بشه تو شو شو Sorry about that. Okay, so now, so this one, for example, gives us AI1, I2, and then with this, I get AI4, I5. And then, so this two. And then this one gives I2, I3. And then I've got I6, I1. What am I doing here? Sorry. What? This is, so sorry. AI2, I3 here. And then AI6, I1. Okay, so this is identified, this is identified. Now this two gives me AI3, I4, and then I've got AI5, I6. Okay. Now there is something very interesting, some very interesting topological thing happens that if we identify these edges, okay, this is called polygon gluings or polygon identifications. If we identify these things, we get a surface, actually. We get a closed surface, orientable surface. So this is a fact. I won't give a proof of this. I want you to think about it for yourself. It's not obvious, actually, and it's not very easy to prove, but it is true. The fact is that by gluing a, for example, regular polygon with two end sides or edges, we get a closed oriented surface. We get a closed oriented surface with genus G given by. So when we do this, we get a surface. It has a genus G. The formula that I wrote, given by Euler's formula. So let me write it like this, given by Euler's formula. So Euler's formula is number of vertices minus number of edges plus number of faces is equal to Euler characteristic, which is 2 minus 2G. Okay. Number of vertices, we don't know what it is. It can be some number. We'll find a range, possible ranges for this. And number of edges is kind of interesting. Let's look at this example. Because we have two n edges, each two are identified. So when we go over the surface, we are only getting n edges because they are identified one by one, two by two, whatever. So in this case, then we have got three edges. Now, what about faces? The number of faces is only one because this is the face that remains. The rest is like from the yesterday's example, we had torus or a sphere. So we get, I mean, let me give you an example like this. For example, if you do this in this case, what do you think you get in this case?
Is that just a sphere?
You get a sphere, yeah. Genus is equal to 0, in fact. This gives us a sphere. There are some other cases that gives us a sphere as well. And this one gives us a torus. It's not obvious to see, actually. G is equal to 1. Not so obvious. But that's the maximum genus that we are going to see. And we can easily prove it now using the formula that we have. So V minus 3 plus 1 has to be equal to 2 minus 2G. And we have to remember G is always bigger than or equal to 0, okay? So let's do this now calculation. Topological calculation now. So we have got V minus 2 is equal to 2 minus 2G. Okay. So if G is equal to 0, if G is equal to 0, we get 4 vertices. Okay. Now, if G is equal to 1, we still have V minus 2 equal to, okay, so G is equal to 1. This is 0, we get 2 vertices. Okay. V is equal to 2. And now you see that actually G cannot be bigger than 2. Because for G is bigger than 2, for example, if G is equal to 2, not possible. Why is not possible? Because, for example, if G is 2, you get 2 minus 4, which is minus 2, then you get 0 vertices. Certainly, you're going to get at least 1 vertices. I mean, that's the kind of worst case, but all of them are identified to 1 point. We saw it in yesterday as well. So this does not happen. And actually, G bigger than or equal to 2 also does not happen. So in other words, this simple argument using Euler's formula shows that now, so far, that we only get 2 types of surfaces. Surfaces with genus equal to 0, which is a sphere, or G equal to 1, which is torus. But we have many, many cases. So we have to see how many cases correspond to a sphere, how many cases correspond to torus, and so on. So that's, so this is a very, if you want, elaborate story, and I'm just telling you it in step-by-step manner because it's a very elaborate story. I mean, we cannot just grasp it all at once. We just have to digest it in a small doses. Okay? So this is as far as genus goes in this case. Now, what is the importance of B? B is very important. Equal to number of vertices. You see, if you look at, so let's look at, for example, in this case, what is this case? I mean, G is equal to 0. We found that for G equal to 0, we got that V is equal to 4, right? We have to see what is the importance of this. I mean, here is the case G equal to 0, for example. So we have got this thing, which is AI1, I2, right? And then AI2, I3. And then I've got AI3, I4, AI4, I5. And then AI5, I6, I5, I6, AI6, I1. Okay, now let's see what, so there is no problem here. We get 1 always because I2 is I2, but we get 1 only if I1 is equal to I3, right? I1 is equal to I3. Now, if you look at this, I4 is I4, this is fine. So I3 has to be equal to I5. Okay. So far we have got what? We have got, yeah, did I write it correctly? I3, I4, I4, I3, I4, I4, I5, yes. Okay. And AI5, I6, AI6. Now here, AI6, I1. So I1 has to be equal to I5 here, only one condition. So how many conditions we find here? So I1 is equal to I3. And this is equal to I5. How many we get now?
N to the 4th.
That's right.
N to the 4 you got, right? Why do I calculate N to the 3 now? I don't know. I mean, it seems to me sometimes I just totally feel really lost. Why?
Well, we have n options for I1 and n cubed options for the ones that aren't in the equality.
Okay. When I was thinking about the lecture, I knew that it has to be N4, but now I see N3, but I trust you. And I trust my earlier, but I cannot see it now. Sorry, I'm just, it's good. This
Well, without any equalities, right? Like we take away all the equalities, we have N6 options, right? N to the 6.
Okay.
Now we're equating two things. So it's like we're taking away two of the powers. So then it's N4.
Right. Okay. Yeah, I agree. But I mean, I somehow it baffles me sometimes. I just I don't know. Anyhow, but now the main point here is that actually this n, this v, really always gives the power of n. So here is the claim. Okay, in a gluing with v vertices, I mean, V vertices means that you did some gluing and you obtained V vertices at the end on the surface, right? With V vertices, we get a term n to the V. Because this number of vertices is exactly the number of free parameters that we have, basically. The rest are zero. So this is a very important statement. It's part of the strategy of the proof. This is very important now. Okay. So using that, then we can just write the thing in the following way. So instead of doing it for 6, I just write it in general now, 1 over n, expectation value of trace of an over root n to the power 2n. I just write it like this, sum n to the power v of sigma over sigma, where sigma is the set of all surfaces obtained by gluing a 2n gun according to this procedure that we showed. Okay, so sigma belongs to sigma, so this sigma is the set of all surfaces obtained by gluing a regular 2n gun. Okay, but I mean, this word gluing now, we know exactly what it means. This is an example of gluing, right? So this is the, so at least this argument shows that, oh, I have to write it like this, sorry. This is equal to 1 over n to the power. This is n, little n plus 1. Yes, let's not forget that. So it's this one. Okay. This is a very, very important formula by itself. It's a very important formula. It's almost the topological expansion itself, but we can just massage it a little bit and get the information we get. Okay, now, any questions, by the way? Cool. Now, what we need to know is what is the maximum possible V, right? Maximum possible number of vertices. In other words, we want to know the highest power of n that can come. So maximum possible n V, sorry, is equal to what? Well, to do this, we just use Euler's formula. Euler's formula said that V minus n plus 1 is equal to 2 minus 2g. And we know that g is bigger than or equal to 0. So maximum possible V happens when g is equal to 0. This you can easily see. So V max happens only for g equal to 0. So this implies that V max is equal to, so if g is equal to 0, we get n plus 1 from the formula, right? Because g is 0 and then. So for g bigger than equal to 1, bigger than equal to 1, obviously you're going to get V is strictly less than V max, which is n plus 1. Okay. Yeah. Okay, so that's okay. So this is good. It means that the order of n here matches this power. Now, the only thing that remains to know is in how many cases we get G is equal to 0. We get genus 0 surface. So it remains, because this sum is kind of elusive rather, because it looks like the coefficient is 1, but in fact, this could be many, many cases. For many, many sigma, we can have V of sigma equal to n plus 1. We have to count for how many sigmas surfaces we will have a genus equal to 0. So it remains to know how many sigma belonging to sigma have genus equal to 0. Okay, so this case, we make a kind of first observation towards answering this question is that this happens if and only if these pairings are non-crossing. There's a lemma here. Pairing gives a genus 0 surface if and only if it is non-crossing. Non-crossing, so i.e. like, so let's look at for n equal to 2. These ones are crossing, so this is not good. I mean, this is no good. This one is non-crossing, these two, and this one is also non-crossing. These two are okay, this is bad. And as we saw yesterday, of course, you can see it right now, this gives us a genus 1 surface, but this gives us genus 0 surface. And this is also genus 0 surface. Okay. And you can look at the case for 6, for example, sides. The non-crossings are these ones. For example, this is non-crossing. What are the non-crossings? This one. And then so this can come here. So what else now we can have?
Like a cross?
Oh, this I already did. No, I want to do non-crossings. I want to see how many non-crossings we are going to have here.
Like you go to like you go to the opposite side with one, and then you go to like adjacent edges with the other.
Yeah, that's right. There are 3 more.
There are a lot more. So let's draw one more here. So Well, what should I do here? So
Top with bottom.
this one,
Yes.
this, for example, and this, right?
No, we already have that.
Oh, I
We
already
need
have
the
that.
we need the top and the bottom sides to be connected.
Oh, yes,
Yeah.
like that. And then we can just do the other ones similarly.
Yes.
So, so this is okay. This is genus 0, non-crossing, non-crossing, genus 0, non-crossing. Okay, so if we believe in this lemma, then what happens is that now we are able to identify one term of the that expansion. So let me write it now. So let's see. So far, 1 over n, 1 over n to the power n, expectation value of trace of an to the power 2n. We saw that is equal to 1 over n to the power n plus 1 sum n to the b sigma, okay? Sigma belonging to sigma. Now I can write it as 1 over n to the n plus 1. I can write it in a totally different looking way, which is going to be interesting actually. So I just write epsilon of g b to the power, sorry, n to the power g in terms of genus. No, that's not what I want. So let's see. I want to write it in terms of. Okay, so let's look at the formula again. V minus n plus 1 is equal to 2 minus 2g. So V is now equal to, so this cancels, so equal to n plus 1 minus 2g. So this is V is equal to n plus 1 minus 2g. So here is, and so n to the b sigma over n to the power n plus 1 is equal to n to the power negative 2g. Okay, so this is all. This always comes up. So I can just write it now as in the following way: some epsilon of g, some strange numbers epsilon, and then n to the power minus 2g. G from 0 up to infinity, but it is a finite sum. It's not infinite because we know that you can only go up to certain genus because of the formula. Okay? So this basically starts with epsilon 0 constant plus epsilon 1 n to the power minus 2, so on. Okay, so that's what it is. Epsilon 0 is equal to number of non-crossing pairings. Pairings of sides of a regular GUE gun. In fact, we can just think of it as non-crossing pairings of the set of indices 1, 2, up to 2n. That's the same thing. So this is the same thing as number of non-crossing pairings of the set 1, 2, 2n. Right? That's just what it is, yeah. So we have to, all we have, because you see, these terms go to 0 as n goes to infinity. It's a finite for each fixed little n. This is a finite polynomial in an inverse, and take the limit as n goes to infinity. This goes to 0, remains epsilon 0. So we just have to find this number. This number is Catalan number. So, and in fact, it's not difficult to prove that. So I want you now to prove it using the recursion formula for the Catalan number that I gave you. Okay, so here is the problem. Show that. Okay, so honestly, this should be actually epsilon g and n. There should be some factor, some little n here as well. I mean, because this depends on this little n, so it should be called epsilon g and n. Okay, so epsilon z, so epsilon n 0 is equal to Cn, equal to nth Catalan number. And this is equal to 1 over, I write it this form now, 2n theta. By showing that so well, I mean, if we didn't have the recursion formula for Catalan numbers, that would be difficult. But if we show a sequence of numbers satisfies the Catalan recursion, and epsilon 0 is 1, then we know that this is going to be Catalan numbers for all n, showing that they satisfy the Catalan recursion. So how we what was the Catalan recursion? Do you remember? It was that Cn equal to, so I believe it was something like C0, Cn minus 1, plus C1, Cn minus 2, plus Cn minus 1, C0. Or something like that, right? And C0 was equal to 1. Okay, so all we have to show now is to show that actually the number of non-crossing pairings satisfies this recursion formula. And proving that is not difficult, because proving this recursion for epsilon n0 is not difficult, because if you have, I'll give you a hint. Should I give you a hint, or you want to think about it yourself? Maybe I better don't give you a hint, right?
Yeah. Yeah.
I better don't give you a hint. Just I want you to prove it, to enjoy discovering the proof. That's better. Yeah. So this can be done. Yes. Okay. So using or putting together all these steps, now we are we know that so the corollary is that limit of 1 over n plus 1, expectation value trace of an to the power 2n as n goes to infinity is equal to Cn. Of course, another definition for Cn was that this is the nth moment. This is the 2nth moment of Wigner's distribution. This is the x2n of Wigner's semicircular law, which is integral x2n. Okay, so this is equal to 1 over 2 pi integral minus 2 to 2 square root of 4 minus x squared dx. So if you think about it, this is really remarkable because this integral, which at first looks like a stupid integral, has to do with all of this combinatorial, beautiful geometry of Riemann surfaces, actually. But this is just the beginning. This is really the beginning. There are a lot of connections like this in random matrix theory, as you may have seen already in some other contexts. Now, we identified epsilon 0g for all g's, but finding this for other values of n is very difficult thing to do. It's extremely difficult. And people are still writing papers for this, actually. I will send you a very nice a chapter in a book. Well, I'll send you the book, but there's a beautiful chapter which really gives you a very good picture of what is known, what is not unknown. So equal to what for? I mean, right. I mean, for example, I mean, what we discussed was only for. Yeah, I mean, this was we discussed it only for g equal to 0, right? For g bigger than equal to 1. Okay. Any questions? Now, one of the things that so far we discussed GUE. I want to give you another problem. I was going to send the problem to you, but actually I can just give you the problem now. So this is consider. So this is problem or exercise, whatever. Consider GOE. This is Gaussian orthogonal also. So this is basically is an n by n matrix, real, symmetric matrix. So orthogonal means symmetric, real, and this is what it is. And I want you to discover what sort of distribution, okay, so with AIJs independent for I bigger than or equal to j. Now I want you to find some good Gaussian distributions on AIJs for what distributions we will have basically trace of 1 over n trace of an over root n squared expectation value is equal to 1. I mean, because this is really C1. So, because if you start trying to prove Wigner's semicircle law for GOE, you want to start with something that actually, in the GUE case, you want to start with something that satisfies this condition to start with. And I want you to find the kind of distribution. So, for example, you might say, make the elements on the diagonal. So, in the complex case, what we discovered is that the off-diagonal elements, which are complex, they have to be complex standard normal. And that had a definition, which was rather peculiar, but this was a definition. And on the main diagonal, they are real standard normal. So in the real case that we have here, what should be on the diagonal and what should be on the off diagonal? For example, is it okay both of them are be normal, standard normal, or you wanna have different variants, for example, between difference between diagonal and off diagonal terms? I want this is a little bit of calculation you have to do. It's a bit of nuisance, but it's good to do it once in your life. So, okay. I think okay, but now I should say there are many different proofs of semicircle law. People use different type of combinatorial devices in order to do this counting, to facilitate the counting. So there are a lot of different devices people use. So I think now we can move beyond GUE and introduce some next terms. So the next goal is to, let me just tell you this and then we just say we are okay now. Next goal is to look at the following matrix integrals: exponential minus n trace of h2 plus g, for example, trace of h4, for example. So we are going to introduce a term, a potential, basically, which is like a quartic at degree 4 now. And we want to see what can we do with this expression. We will see that actually these guys also have topological expansions, and there are a lot of nice things you can say about these things. But we need some definitions, some conventions. So it should be divided by 4. Normalization is 4, but that's okay. Yeah, so that's the idea. And after we write down the expansion for this, we will do Schwinger-Dyson equations. And then there is one more topic before we start the project, which is basically this bootstrap technology, which is people are using now in many different fields. Also in standard classic statistics, people have used it, but I'm not a statistician, so I'm not really familiar with that. So yeah, that's it. You have any questions? Okay, if not, I think tomorrow we still can meet, same time at 2. And I will try to see what's the next logical step. Maybe we go through this and then try to find topological expansion for these things, and then we go from there. And I will send you that book by there's a book by Zwankin and Londo. It's called Graphs on Surfaces, which is which is very interesting. Okay, guys, thank you very much.
Have a nice
Have a
day.
nice day.
You too. Yeah.